number. Right? But then this is where it becomes a polynomial. So when n equals 0, anything to the 0 is 1, and this whole thing is just a number, it's just a constant. But when n equals 1, this is x to the 1. It's got a constant in there, but it's basically x. When n equals 2, it's x squared. N equals 3, it's x cubed, etc. So you're turning this function into an infinitely long polynomial. Okay? Let's write the first few explicitly just to give you the idea. So how do you take the zeroth derivative of a function? Well, the zeroth derivative in this case just means the function. All right? So the first term is just the function evaluated at a over 0 factorial. What is 0 factorial? Well, it's 1. Okay. And then we have this part is x minus a to the 0, but anything to the 0 is 1, right? So it's really just 1. All right. So the first term is just the function evaluated at a, just the constant value. What is the function at a? Second term plus. Now we're doing the n equals 1 term. Now we need the first order derivative, the first derivative, df dx, evaluated at a. So you take your function, take its derivative, and plug in a for x. 1 factorial is just 1. And then you say x minus a to the first power. Okay. So now you have a linear term, which is exciting. That's kind of what we're looking for. And then you could keep going. Next would be the second derivative, d2f dx2, evaluated at a. 2 factorial, 2 times 1 is 2. X minus a squared. Now you have an x squared term. And you could keep going, plus, and then dot, 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 dot. And you could go on forever. Okay? So now maybe you're starting to see how we can use this to make something linear, right? It looks like that. What if we could just keep those terms? Okay? Let me show you what it looks like when you really do this. Here we go. So let's pull this down here. And I've plotted a crazy function for you, this one here. So this function is 1 minus cosine x over 1 plus x squared e to the x. This is one of my hobbies. I just make up functions. Okay, so in this function you can see it has sort of a double hump, very complicated function. This would be, it's very nonlinear, clearly, and it would be a really hard differential equation if you equated it to mx double dot. It'd be very hard to solve. So what we're going to do is pick a couple points and expand and show how we can linearize this around different points. So let's look first here at x equals minus 3. So let's bring that up onto the thing. So this is the function at x equals minus 3. Okay. So now let's look and say this will be f of x, and this will be sort of the numerical value. So the first term is the function evaluated at minus 3 over 0 factorial equals 1 times x minus minus 3 to the 0, which is 1. So it's really just the evaluation of the function at minus 3. And you can see here it comes in at like just below 0.2. Sure enough, there it is. So the 0th order term is always just a constant, 0.19. Let's see how our approximation looks at this point. Not very good. Okay? So it's basically just a constant, and you can see it's that's the 0th order approximation. Okay? It's really good right at that point, and it's not good anywhere else. Okay? So now let's look at the next term. So here is n equals 1 term, df dx. Now we've taken the derivative of all this. That's a lot of work. That's a quotient, and that's a product, everything. You take that whole derivative, you plug in minus 3. But again, this is always just a number. 1 factorial is 1. And now we have x minus minus 3 is x plus 3 to the 1. So now we can see this whole thing now together is a linear. It should be a line. So let's plot it and see. And now, yes, so here's the line. This is now the approximation. And now you can see just this linear expression is a very good description of this curve right here. Right? If I promised I was going to stay in this box, and you wanted to describe the motion if this were a mass on a spring, this would be just about as good as this. And this would lead to a differential equation we can solve. Right? Let's keep going and see how much improvement we get. As you add more terms, basically you get a more detail and you get a better fit. So here I took the second derivative of this big nasty thing. I plugged in minus 3, 2 factorial, x minus minus 3 squared. Looks like that. And if you plot it with the second order, you see, watch this part right here. You get a little bit more curvature. But you can see it didn't really make much of a difference. Especially if you're just right in here, the linear part was enough. Okay, so we could have stopped at the first term to linearize it, and we would have gotten good answers. Let's look at another spot. Let's look at x equals 2. right here. So x equals 2 comes up. That's right on a very curvy part of the approximation. And let's look at the 0th order term. That's just the function evaluated at 2 over 1 times 1, 0.1143. And yeah, sure enough, it's about 0.1143. And there's the approximation, not very good, right? It just goes through that point. Now, let's look at the linear term. And you can see now we have df dx evaluated at 2 over 1, x minus 2. There's the numbers. Plot it, and here it is. This is the line it predicts. And you can see it does describe the curve, just in a much smaller domain, right? So if you were to stop here and call it a linearized version, you'd have to be more careful where you apply it. You have a smaller range over which to apply it. Here, we can see if we add the second term, we get a better description. So here, the second derivative evaluated at 2 over 2 factorial x minus 2 squared. There is the second order term, and you can see now it's doing this. And you see actually that is a big improvement. It describes it a lot better when you have the x squared in there. But it would lead to a differential equation that would not be linear. So in physics, what we do is to linearize, we just keep this term and we keep this term. Whether or not it describes enough of the domain, that's something specific to each problem. But mathematically, this is what when we say we linearize something, this is what we do. Technically, we're applying a full Taylor series and just cutting it off after 2 terms. Okay. So now we're going to show you how to do that in a real problem.